Algebra II students. Today's lesson is a continuation on our chapter on functions. So we've been talking about what makes a function over the last few lessons. We've talked about discrete functions and continuous. We've talked about one-to-one, on-to, or both. Now we're going to learn different special functions and we're going to graph them. So this is actually the first part in a three-part series that we're going to do today. Today's lesson is specifically going to talk about piecewise functions, but we're going to look at the upcoming lessons ahead for a minute. So these special functions are all part of lesson 2.5. We're going to talk about step functions. So when we graph the step functions, you can see that it appears to look like a set of steps. Those come from what's considered our greatest integer function. So again, these are going to be brand new functions for you that you've never worked with in Algebra 1. Our second function is a constant function. Now this one is a familiar function to you. So this is when f of x is equal to some constant, whether it's 4 or 5, but it never changes. It constantly remains the same and level at that value. Our third function that we're going to talk about is the absolute value function. And you can see that the absolute value function makes a V-shaped. It comes from taking the absolute value of maybe x minus 4, or 3 times the absolute value of x plus 2. But it's coming from absolute values. So you get a sharp V shape when you see that absolute value function. The last one is the one that we're going to focus on today. Now we're going to talk a little bit about constant functions, but that's just a review. The last one that we're going to talk about specifically today is the piecewise function. Now, what is unique about a piecewise function is that you can see that it becomes pieces of different graphs. In this piecewise function specifically, you can see 1, 2, 3 different pieces of graphs. So that comes from 3 different functions. It doesn't always have to have 3 pieces. It could have 2 pieces, or it could have 5 pieces. But it comes from different rays, segments, and curves. A piecewise function will be written in a format that will explain which function you're looking at. So maybe our first function was 2x plus 3. Our second function was a constant at 2. And our third function might have been 1x minus 7. But it gives you 3 different pieces. Now I'm just guessing what those are off the top of my head. That's not what those actual pieces are, but this is just what a generic piecewise function looks like. All right, so we're going to go through a couple examples, and then I'm going to refer you to your worksheet that I uploaded for you, and we're going to work some of those out together. So this first example, it says graph f of x is equal to -3. Notice that with this function, there is no variable. When there is no variable present, that means that either you're going to get a vertical line or you're going to get a horizontal line. In this case, we have our f of x, which is our y equals -3, meaning that if there were an x there, it is flattened out. So there is no x. This is just our constant. Our x value would actually be 0, meaning that our slope is 0 of this line. So what we get here is if we had to plot points, no matter what value I choose for x, if I choose an x of 1, y is constantly -3. If x is -2, y is consistently -3, giving us that horizontal line. Constantly at -3. Now, if I asked you to find the domain of this value, the domain would be, look, I have a value at 0, I have a value at 4, at 5, at 10, at 100. So my domain for constant functions are always going to be all real numbers. As far as my range is concerned, My range is going to be the only y value that is present. The only y value that we have is -3. So my range is going to be all y values such that y is always equal to -3. So that is a constant function, and that's how we find our domain. Remember, domain goes left to right, and range goes up and down. All right, so let's look at what a piecewise function looks like. So here is an example of a piecewise function, and we're going to just talk about the components very quickly. So you can see real quick, I have a thin red function and a thin blue function here. Now notice that it follows the vertical line test. So anywhere I draw a vertical line, my vertical line is only touching that function once. So it is indeed a function. All right, now this one says our rules for that function is graph 2x plus 3 when x is less than 1. So here's that boundary line 1. You can see that that red line meets the blue line at 1. So if I look at this red line, it has a y-intercept of 3 and a slope of 2. So this is the graph of 2x plus 3. For my second graph, it is constant at 5. I know that's hard to read on the graph, but this is the constant at 5. This graph is going to be consistently at 5 when x is greater than 1. So what we have are two pieces of two different functions, 2x plus 3 when we're less than 1 and 5 when we're greater than 1. So if I needed to do the domain and range for this, you can see left or right, I'm going to have a value everywhere except at 1. There's no value at 1. There's a little open circle here. So my values of my domain are going to be all values of x such that x cannot equal 1. And the range is, now look how far I go vertically. So from here, I go forever down. So it's always going to go all the way down, but it's going to have to stop as I move forward or upward at 5. So my range is going to be all y values such that y is less than or equal to 5. That's my domain and that's my range. Remember, domain goes left to right, range is up and down, what you actually see graphed. All right, now I'd like you to start working some of these problems with me. Looking at that graph paper that I gave you on Google Classroom. If you look at number 1, these are guided practice. So these are going to show us how to actually make that piecewise function. So my first function, f of x, is equal to 2. Now you can see this is just a constant. There's no second function or third function. This is just a constant at 2. So I'm going to graph where y is equal to 2, and I'm going to sustain that continuously left and right. So we have that constant function. So my domain on this function, left to right, is going to be all reals. It goes forever. But my range is going to just be the y value 2. So I'll write that y such that y is equal to 2 for my range. And that is my constant function. Now if you move on to number 2 on that packet, it asks us to graph f of x is equal to x. Now this is a special function. Now it's not a constant or a piecewise function, but this is actually the identity line. And this is considered the identity line because no matter what the x value is, the y value is constantly the same value. That makes an identity. So if I look at this and I want to graph this real fast, I can see that my slope is 1 and my y-intercept is 0. So I'm going to graph that. Or when x is 1, y is 1. When x is -1, y is -1. And I get that identity line of y equals x. Now, if I want to talk about the domain and the range of this line, the domain, as I look left and right, is going forever. As I look at the range, how far up and down, it's also going to continue to go up and down forever. So for this identity line, the domain and the range both are all real numbers. All right, so let's look at that number 3 that you have on your worksheet. It is f of x is equal to negative x. So this is actually the odd identity. And why it's the odd identity is because of the negative value. So if I do a quick slope-intercept, my slope is -1. My y-intercept is 0. So I'm going to start at 0 and graph out that slope of -1. So you can see it's the exact opposite of what we just had. So for the identity, when x is 1, y is 1. But for the odd identity, when x is 1, y is -1, and so forth. So that gives us the opposite diagonal line. But when I look at the domain, how far left and right we go, it continuously goes forever left and right. And my range up and down continuously goes forever. So for both of those graphs, we're going to have all real values for our domain and range. All right, now let's move on to number 4. So number 4 does look like a constant, but what they're doing with number 4 is they are mapping out a specific domain for this constant function. So it says that we want f of x to equal -4, but here's the rule. The rule is only when x is greater than 0. So if I go to my graph here when x is 0, we're not going to have anything to the left of this value because I only want values when x is greater than 0. So it's saying when x is greater than 0, our function is always -4. Now, at 0, it's not going to be anything because this stipulates x has to be greater than 0. But as soon as x is 0.1 or 0.01 or 0.0001, f of x is going to be -4. When x is 1, we're at -4. At 2, at 3, at 4, at 5, forever, my function is going to be at -4. So you can see for this function, I'm only seeing a piece of the graph. I'm not seeing the entire line. I'm only seeing the part that's given by this domain up here. So when I list my domain, I'm not going to have all real values. It's not going to go forever from left to right. My domain is going to be all x values such that x is greater than 0. For my range, I'm still, no matter where I am, after 0, I'm always constantly on -4. So I would read this as all y values such that y is equal to -4. Okay, let's do one more like this before we piece 2 or more graphs together. So this is the function 4x minus 1. Now the stipulated domain on this is when x is -2. So really I'm going to have kind of like this imaginary boundary wall here. And I'm not going to have any values over here, none at all. All right, now for this one, you can see that I have a slope of 4 and a y-intercept of -1. So I'm going to plot that on here like I normally would, but I'm not going to show this part of the graph at all when I'm done. So my y-intercept is -1, but I have a slope of 4. Now typically I would go up 4 over 1, but I'm in this region that I'm not going to have any part of that graph there. So I'm going to go down 4, 1, 2, 3, 4 over 1. I'm going to keep going down. You can see I'm losing my graph here. 1, 2, 3, 4 over 1. And that's really where my graph's going to start. And I'm going to continue down following that shade to the left. Now really, none of this actually is going to exist. We're only seeing the part of this graph that's less than or equal to 2. So here's where this graph's going to start, and it's going to continue to the left of that. So that's going to make my domain all values of x such that x is less than or equal to -2. You can see how those two match. And our range is going to be all y values. Now it has to start where we are here. So if I plug -2 in here, that takes me to -8 minus 1 is -9 is my highest y values, and then they get smaller from there. So my domain and range isn't going to be all reals on this one. Of course, if I would take this stipulation away, it would be all reals. But because that we have that there, and that's part of our restrictions or our rules, our domain is also going to be restricted as well as our range. All right. So this should be number 5 on that worksheet packet with you. If you go to number 6, you're going to see our first true piecewise function. So for this function, you can see 2 different pieces of graphs. All right, so we're going to graph 1/4 x plus 2 if x is greater than 4. And we're going to graph -3 if x is less than 4. So what I'm going to do is I'm going to put an imaginary boundary line at 4. Now that's not part of our graph. I just know that at one side of that graph, I'm going to be looking at 1/4 x plus 2. At the other side of that line, I'm going to be looking at the constant function -3. So for the first function, I have a slope of 1/4 and a y-intercept of 2. Now I'm going to base it off my axes, but I'm not going to graph the whole thing. So my y-intercept is 2, and I'm going to go up 1 and over 4, up 1 and over 4. So for this graph, I want to be greater than that boundary line, not equal to it. So when I hit that boundary line, I'm going to use an open circle. And I'm going to continue to the right because x is greater than 4. So I'm going to continue this linear graph to the right. Then I'm going to graph the second part of the line, or the second part of the function. So the second part of the function is -3. So that's just the constant function y equals -3. Now this constant function is going to be to the left of 4. So when I go to 4, I know that I need to be at -3, but I'm not going to include 4. I'm going to include everything to the left. So I'll continue this line to the left. So this is my line 1/4 x plus 2, and this is my line -3. Notice if I if I take the vertical line test, it passes everywhere, but I do have a gap here in my range. So for my domain's going to have all values left and right except it's not going to have a 4. So my domain is all values of x such that x does not equal 4. And my range is going to be in twofold because I have a big gap here where I have no values. There's no values here. So for that reason, I'm going to have all y values such that y is equal to -3, and I'm going to union that with y is greater than +3. So you can see that there's a gap. There's nothing below -3, and there's nothing below 3, but there's a gap in between. So my range is a little bit different there than you're used to. Let me just get rid of this. So there's our function graphed with our domain and our range. All right, let's look at another one. So we have this piecewise function. I have x plus 2 if x is greater than or equal to 4. And I have negative x minus 4 if x is less than 4. So I'm going to go ahead and put in my generic boundary line, again at 4. Got a little crooked there. All right, so for my first function, I'm going to graph x plus 2. So that function is going to have a slope of 1 and a y-intercept of 2. So if I graph that, 2 and a slope of 1. Now notice that I want this function to be to the right of 4. But I also want it to include 4. So I'm going to have a solid dot when I get to 4, and I'm going to continue the trend with a slope of 1. For my second function, I'm going to have a slope of negative 1 and a y-intercept of negative 4. So I'm going to start here, 1, 2, 3, 4, and my slope is going to be a negative 1. So it's going to go down this direction. And this time it's not going to include it, but it's going to point to the left. Okay, so when I graph this to the left, it's going in this direction. So this is my negative x minus 4 graph, and this is my x plus 2 graph. Notice that once I get them drawn, my arrows are always going in the opposite directions at the ends. If they're ever going in the same direction, then you probably have done something wrong because that will no longer make a function. Let me even refer back to our last example. Notice that one is pointing to the left and one is pointing to the right. You want to continue to do that. Point to the left, point to the right. Now for this guy, our domain, notice that I have every value, including 4 this time, left to right. So our domain is going to be all real values. Our range, however, is going to not have any values below this value here. So that's 4 in the second graph. So that's at negative 8. So all y values such that y is greater than negative 8, not including it, but greater because they're both going in an upward direction. So there's our domain and our range. All right, so our next graph, f of x is equal to negative 2/3 x minus 8. So you can see we're going to have to add a little bit onto our graph. And that's if x is less than 3. So this is going to be our left portion. And then we're going to have 1/3 x if x is greater than negative 3. That's going to be our right portion. So this is going to mean the first one's going to point to the left. The second one is going to point to the right. So if I go to my slope-intercept, my slope of my first graph is going to be negative 2/3 with a y-intercept of negative 8. And my slope of my second graph is going to be 1/3 with a y-intercept of 0. This time, my boundary line is going to be at negative 3. So I have nothing. Not that I won't have anything on negative 3, but you can see that I don't have anything included. So I should have nothing on negative 3. One graph's going to be to the left, one graph's going to be to the right. So I'm going to graph the first one. When x is negative 3, I'm at negative 8. So 5, 6, 7, 8. And it has a slope of negative 2/3. I'm going to go up to over 3. And I hit the boundary line, but I'm not including the boundary line. And I'm going to go with the next trend up 2 over 3. And then I can continue graphing that to the left. So this is my negative 2/3 x minus 8 line. And then to the right is 1/3 x. So this will have a y-intercept of 0, and it will have a slope of 1/3, or I can come down 1 and over 3. It's not going to include that boundary line either. So I'm going to put a circle on the boundary line. Now this one should be pointing to the right. So I have the orange graph to the left, which is -2/3 x minus 8. And the purple graph is 1/3 x, and it is pointing to the right. So this is our piecewise function. I have two pieces to this graph. Now let's talk about the domain and range. So left to right again, you can see that I should have every value except I am not going to have -3. So it's all values of x such that x does not equal -3. And my range, since both graphs are pointing up, and there is a little bit of overlapping in the range, here I'm going to have all y values such that y is greater than, and this is going to be at -3 here on that orange graph, so that's going to be greater than -6. That's our domain and our range. So I've got you to number 8 on that worksheet. What I want you to try now is 9, 10, 11, and 12. Once you've completed those 4, upload those to Google Classroom for me so I can check those to see how you are doing. I hope you have a great day. Tomorrow's lesson will consist of greatest integer, the special function greatest integer.